I have a couple of questions before I begin. So how many of you are computer scientists? Can you raise your hand? All right, that's good. Is there anybody who's familiar with neuroscience? Please raise your hand. That's good. That's very, very good. Okay, there's 1, 2. Okay, that's not that great. Okay. Is anybody familiar with linguistics? Okay, I gotta be careful. All right, that's good. All right. So anyway, so my talk is going to be divided into 2 parts. In the first part, I'm going to give you some high-level ideas or the views of my own on how the deep learning or the machine learning in general should or will advance. And then in the second part, I'm going to go into a bit more details of my recent research in machine translation. So, one thing that you notice, if you go onto Facebook or I guess Naver Line, I don't know, it probably has the kind of news recommendation there as well. One thing you notice is that there are so many awesome things happening every day with the machine learning and deep learning. You see the awesome convolutional neural net that can recognize objects better than usual humans. And then Baidu, about a couple of years ago, announced that their speech recognition system can transcribe speech either in English or Chinese better than the humans can transcribe speech. And then Google DeepMind has been making the Atari game amazingly, let's say, interesting by building all those awesome Atari game players that can play Atari games better than humans in general. Of course, it's kind of difficult to tell why that's that exciting, but that happens. And then we have the awesome language model that can generate sentences as well as, in fact, better than most of the humans. And then on top of that, when you see the NVIDIA giving a demo of their self-driving technology, all they have is a single neural net that's going to look at a front view and then rear view camera, and then just generate the steering wheel angle, as well as see whether to hit a brake or not. So all those things are super awesome. And then it almost makes us, feel like that, oh man, like the machine learning is almost there. Like the artificial intelligence must be right around the corner. But at the end of the day, this is not what we really want, right? What do we want? What we want is something more like us, something more like humans. So in my case, I have one visual cortex, so that's going to correspond to those awesome convolutional neural nets. I have a single auditory cortex, right? So that's going to correspond to awesome speech recognition system. And then I have a memory that is going to be used by all those different tasks that I can perform. And with the language model, I'm going to say something, like to write something, and then, based on who I'm talking to, I'm going to change my style as well as the selection of vocabularies. And then I have the pretty good motor control system so that I can drive and manipulate objects as much as I want. So what we really want is this one system that has a lot of different modules, and those modules will interact with each other in order to solve a much more complicated or sophisticated task. And then by doing so, those modules are going to share the knowledge across different tasks, and then they're going to get better individually as well. And obviously, not all of them are going to be neural nets. Some of them are going to be just fixed engines, such as the search engine, right? So what I'm suggesting here is that I think we are at the point where we need to shift the paradigm in how we view deep learning or the machine learning. So far what we've been doing is that, so we have a kind of problem that we need to solve. Let's say I need to build a question answering system. Then what I'm going to do is I'm going to design a very nicely and then sometimes pretty complicated neural net to solve that problem, and then collect a lot of data, train the neural net out of it, right? And then, if I want to solve another problem that is, let's say, document summarization problem, then I'm going to collect the data and then build a new neural net and then train the neural net from scratch using the collected data. And then that neural net is going to have nothing to do with the previous question answering neural net. So that's what we do these days. That's what many of you are probably doing at the moment. But what I feel we need to go into is that we need to now build a neural net for each of the functions we have. Now, what do I mean by function? We use functions every day when you, let's say, code something, right? Because we're in a software company here. So what we want is that we want to be able to have a neural net that's going to perform certain function, and then we should be able to compose them in order to solve higher level tasks. And then those modules or the functions are going to be used by, let's say, used over and over by the multiple tasks depending on how those tasks are going to require those modules. And then again, those are going to the mixture of the trainable networks as well as the fixed modules, because we don't have to replace everything with neural nets. I mean, that'll be good for my job security, but that's not really what we want. We don't have to replace the whole search engine with a neural net. It's pretty likely that we won't even be able to do so. So let's take some examples. So let's say I want to build a question answering system. What I don't want to do is build a neural net and then train it from scratch. What I want is that I'm going to use the existing, very well-trained language model and speech recognition system to understand the question given by a user. And then, based on that understanding of the question, I'm going to ask my awesome memory networks to retrieve all the relevant information from what I have stored. And then those information could have been stored by other modules as well. And then those modules do not necessarily solve the question answering module. Those are just saving all those informations. And then based on the question and the retrieved information, I'm going to reuse the language model, which was, again, pre-trained, right, with the amazing amount of data to generate a response. What would be a second example? Let's take the self-driving car. Now, what I'm going to use is the convolutional neural net, likely, like pre-trained on the ImageNet data set or the much larger data set you can get, and then use that to sense the environment, right? So I'm going to look at the front view, and then rear view, and then side views. And then, of course, I need a speech recognition system there as well, right? Because I need to understand what the passenger or where the passenger wants to go. And based on that understanding, I'm going to use the memory in order to plan a route. So, okay, what is the most efficient way to get to a destination? And based on that, again, the controller module, which is again separate, right? The controller module was trained to manipulate or control any kind of things that you can think of. And then the route as well as the vision is going to tell the controller how to drive a car every single moment. So, it seems like, okay, so maybe, it's all solved, right? We know how to train the convolutional neural net very well. We know how to train the speech recognition system very well. People have been working on the memory, like memory augmented recurrent neural net for some time, and then we know how to control pretty well. But unfortunately, this kind of simple composition of neural nets is unlikely to work. Why is that? Let's think about, like what happened when you were growing up, when I was growing up. Our visual cortex develops, largely during the first couple of years of your lifetime. And then during that time, you absolutely have no idea how the visual cortex, or in the case of the artificial neural net, convolutional neural net, is going to be used in 20 years later, or the 40 years later, 50 years later. So when my vision system was developing, it didn't really know that I was going to use that to drive a car and then need to detect the pedestrians as well as other cars that are driving at 120 kilometers per hour or so. And then also my auditory cortex developed in the first few years, listening only to Korean conversations. And like my auditory cortex really had no idea that I'm going to move to Finland in about 22 years, and then it's going to hear Finnish, and then we'll have to learn how to understand what they are saying. But somehow I use that, well, in the latter case, not that well, but I can still use it. Now, what's the gist of that? Those stories is that the target tasks are often unknown at training time. So at the moment, because we're looking at a very, very fine-grained single task, we have a kind of illusion that we are going to know everything about how the module or the neural net is going to be used in the test time. But that's a big illusion, especially if we go into the regime of the lifelong learning. There's absolutely no way we can know how those modules or the neural nets are going to be used in the future. And then we have to have a way to use it better. And then furthermore, because we don't know how they're going to be used, we cannot really define the input and output well in advance. And the third one is not that important. So what do we need? What we need to do is we need to be able to actually go beyond the traditional paradigm of having an input and output, but we need to be able to access the internal of the neural net. Why is that important, right? Because, okay, so in short answer is that the neural net, the internal hidden activations of the neural net capture all those rich information about the input or the whatever that is given by the environment or the other neural net. The reason is that if you think about what supervised learning does, it's going to be, like it can be a bit confusing, is that what neural net does is to figure out what should be dropped. What kind of information should be removed from the input. So let's say, I have the image of a panda here, and then what I need to do is get the label saying panda. What I need to do is I need to learn to remove all the background. I need to learn to remove all the unnecessary details that are there that's going to confuse me when I say panda, right? And what it means is that, in fact, within the neural net, we have actually a lot of information there. And then in order to remove the information, it needs to extract out or disentangle all those factors of variations. So that's why neural net hidden states are capture all those rich information, and then that's what we need to exploit. Instead of just looking at the input and output, because we cannot really design it perfectly in advance, we need to be able to use the internals of the neural net. So there's a good news, is that the neural nets are completely transparent. When people ask you or they tell you that the neural nets are not really great for a certain application, saying that like neural nets are black box, then you gotta, they are just lying to you, completely lying, right? The reason is that let's say I have some sophisticated neural net, either trained or not, and then I'm going to ask you to, okay, give me any kind of complicated input. I'm going to get it, and I can give that person back every single bit of whatever is what is happening within the neural net. We can always do that because that's software, right? So it's in fact a complete transparent box. So that's the good news. But the bad news is that it's extremely hard to understand. So I did train a simple recurrent neural net language model on a small corpus, and it has a 1,000-dimensional hidden state. And then I wanted to show that these structures, the structures of the hidden states are really great. It's like well stretched out and so on. And then I did some visualization. I was like, yeah, okay, I don't see anything. Do you see anything here? So the input sentence was, there is a storm on its way. And then this is the 1,000-dimensional hidden activations. Yeah, I don't really see anything, right? You probably don't as well. So I thought that, okay, looking at a single example is not a great idea. So I'm going to look at the multiple examples and then do the dimensionality reduction. I use the t-SNE there. And then I visualize the four sentences there. And then I was trying to find some kind of pattern, right? So, okay, the words is are kind of close to each other. And then end of the sentence seems to be kind of far away from the center. But, really nothing, right? You don't really see anything because humans are just inherently bad at understanding those high-dimensional vectors unless it's very well structured, like an image. And furthermore, because of the nature of the neural nets, or how we build neural nets these days, is it utilizes a distributed representation. What it means is that it actually gives us a exponential combination of the hidden. It requires us to inspect these exponential combinations of the hidden units in order to see what's going on there. And then with 1,000 units, if you think about the exponential combinations of them, it's just simply impossible. But we know how to solve that problem. That is, we're going to use another neural net. Because one thing we know how to do really well nowadays with a deep neural net is to train a model to look at the high-dimensional vector and then output yet another high-dimensional vectors. That's precisely what we do every day with the neural nets. So what we're going to do is we're going to train another neural net that's going to look at the internal of the original neural net in order to understand it or interpret it, and then send out the signal that's going to manipulate the behavior of the underlying neural net. And we can do it because we know how to train those neural nets very well. And then these days, we can even train neural nets with an arbitrary objective that may not even be differentiable because there has been a lot of advances in the model-free reinforcement learning algorithms as well. Unfortunately, this idea was rejected by NSF last year, so I'm refining it and I'm going to submit it again, and let's see if NSF reviewers are going to buy it this year. So eventually, in order to build that kind of, let's say, system with the multiple modules where each of the module is going to be either manually engineered or trained, what we really need to do is train a neural net to use another or the set of other neural nets. So this reminds, if you're familiar with the RL, this reminds you of the options as well, right? So this is a very generic idea. And then in fact, if you find the root of this idea, it's just a software engineering. That's precisely what happens with the computer science. People were building a software, given a problem, from scratch every time, but eventually they realized that we realized that that doesn't make any sense. We should be able to reuse the existing components and then use the APIs via web or something. And then essentially machine learning, we are running into that regime as well because we now have the ability to solve much more difficult problems than the problems that we are solving nowadays. So as examples, I'll give you some of the, I'll give you some brief introduction to some of my recent research. So the first one is on how to make the imitation learning more efficient. This is the work together with my PhD student, Jiakai. So you probably have heard about the supervised learning a lot and then use it almost every day if you're doing anything machine learning. You've probably heard about the unsupervised learning because so many of those, let's say, world-class researchers like Yashua Bengio, Jeff Hinton, Jan LeCun, those people are just saying that the unsupervised learning is the future. I don't know why, and then I don't even know, what unsupervised learning is anymore. And then you probably heard of the reinforcement learning, which is on the other extreme, where you're going to get a very sparse reward, and the learner is going to just interact with the word as much as he can in order to learn to survive in the word while maximizing the reward. But those three are not the only paradigms, though they are major paradigms. So one of the another type of learning paradigm is called imitation learning, which kind of bridges between the supervised learning and reinforcement learning. So in order to make sure that avoid any kind of mismatch between the training and test time, in imitation learning, we're going to let the learner interact directly with the word. And then whenever a learner interacts with the word, supervisor is going to just intervene and then trying to give a correct action in addition to the very sparse reward the environment gives. And then it augments the issue with the sparse reward or the weak learning signal problem from the reinforcement learning. But the obvious disadvantage you can see is that, okay, where do we get the supervisor, right? And then the supervisor is going to be always a human at the end of the day for now. And then there is an issue with human supervisors because humans are really fragile. They are emotional. They get super easily frustrated, and then they make so many mistakes. So what we need to do is to make sure that the humans are not frustrated, not exhausted, and then, makes the minimal set of the mistakes. So what we decided to pursue is to make the imitation learning query efficient in the sense of, okay, we want to minimize the number of queries to the supervisor. How can we do that? We're going to build another layer between the environment and supervisor that is called safety net. That's going to look at the word and then decides whether the current state is safe or not, right? If the current state is deemed safe, we're going to let the learner directly interact with the word. But if the safety net feels that, okay, so the current state is too difficult or dangerous for a learner, then what it's going to do is it's going to query the supervisor so the supervisor can intervene and then let the learner learn from that potential mistake. And then, this is a great idea, right? I thought it was a great idea, but of course there are a few questions that need to be answered. First is that, okay, where do we get the safety net? And then, isn't safety net just another human? And then that human is going to be again frustrated and exhausted. And then the second question is that, okay, what kind of impact are we going to have on the learnability or the performance of the learner? So what we decided was that so we're going to train another neural net that is called safety net to look inside the learner, original learner, and then decide whether it's a dangerous or safe situations. As I said, the reason why the safety net wants to look at the internal is that there is the information that is being lost on the way, but there is going to be some information left that can be exploited by another neural net. And then whenever that safety net is going to say, okay, the learner is about to make a mistake or the situation is dangerous, it's going to transfer the control to the supervisor while collecting the data. If the safety net says that, okay, learner is going to do well, then we're going to let the learner just interact directly with the word. So in details, what we do is we're going to prepare the initial supervised learning data set and split it or partition it into two sets. One is D0 and D0S. We train the initial learner, pi0, using D0 in a supervised way, and then train a safety net, which I call it phi0, using the new data set. How do we train it? We give the target as the difference between the learner's prediction and the ground truth annotation from the D0S. Now, you can see that the safety net is effectively trying to estimate per example generalization performance, or you can also view it as a value function, where the value is defined with respect to the performance of the original learner. And then once we train a safety net, we're going to let both of them drive, right? Drive in a track or, like to solve some problem. And then whenever the safety net says, okay, this learner is going to make a mistake, supervisor, you need to intervene. And then meanwhile, during that time, we're going to collect additional data because those data are the ones that the learner is going to fail and the learner needs to learn more from. And then based on that, we aggregate the data, repeat the whole thing over and over. This is not an important thing. So let's see, can you read whether it says by human? Yeah? Can you? No? No one can read it? Some can read. Some can read. I think those are the young people. Yes. So if you can see, yeah, we should have used a different font color. Whenever the situation is kind of complicated, as in there are many cars around or there is, let's say, sharp curve, the safety net is going to transfer the control to the supervisor. In our case, we could make the Oracle controller because we have the access to the all internal states of the game. And then, while it's driving, whenever it says by human, we're going to collect more data for those difficult, let's say, situation, and then we retrain and so on. So how does it work? So this is the y-axis here is the the average number of the laps without any crash. So we're going to let the car drive 3 laps at most. And then this is the number of the dagger iterations, as in how many times we're going to recollect the data, aggregate it, retrain the learner, and so on. So at the supervised learning stage, everything stays same. If you look at this purplish color curve, that's just supervised learning, increasing the data over and over, like they increase the data 4-fold. And then you see that it doesn't really help because, supervised learning, there is a clear mismatch between training and testing. And then the learner doesn't really get to learn for the situation in which learner is going to get in. Whereas this proposed safe dagger, where we collect only the difficult examples every time, we see that it rapidly improves. And then if you look at how often the safety net intervenes, by using the safe dagger, the amount of time the safety net intervenes drops rapidly because those times are precisely the ones that are going to be used to train learner in each iteration. So eventually what we saw was that if you do it further, then the learner is going to learn perfectly to drive without requiring any kind of intervention from the supervisor. Now, this can be used for a lot of other situations as well, right? Maybe the messenger, or like the automated messenger or chatbot or something like that. But we'll see. So next one is on neuro-machine translation, and then especially on the idea of the trainable decoding. And this is the work together with Jiatao Gu, who was visiting me, and then is a PhD student at Hong Kong University, and then Graham Nubik, who's now a professor at CMU. Back then, he was in Japan, but well. So what is the idea of trainable decoding? So again, when we train a translation system, you don't necessarily know how those systems are going to be used. So you think you know, but you usually don't know. Let's say I have a translation system, but what I want to do is to translate a conversation. And then what it means is that I want to minimize the latency between the utterance and then translation. And also, maybe I want to get as concise translation as possible. Another use case, let's say I have a translation system. I'm going to translate, let's say, the article from the Wall Street Journal, but now the consumer of the translation is going to be a primary school student. What I want my translation to be concise and at the same time of mostly frequent words. I don't want it to, let's say, spit out a word that is never used and there's absolutely no way primary school students know. So there are a lot of interesting type of the decoding objectives that you can think of, but except that you rarely know. And even if you knew, it's very unlikely that you'll be able to gather the training examples for the specific decoding objectives. And furthermore, decoding objectives can be arbitrary, meaning that it may not be non-differentiable. And yet another, even if we decide to go for the RL algorithms to solve this issue, RL algorithms just don't work well. So what we decided to do was, okay, so then we're going to just train a neural machine translation system with whatever the data we have to just maximize the log likelihood. We're going to just train it as well as we can. But as I said earlier, as we train, what this neural net learns is not only to output a good probability distribution, but it's going to capture all those rich information about the source and target sentences on the fly. So on top of that, we train a neural net that is going to be much smaller than the original neural net that works to bias or manipulate the behavior of the underlying neural machine translation system to maximize our actual decoding objective. So we did two research work on this topic, and the first one was a real-time translation, which was motivated from the simultaneous interpretation. So if you go to those international meetings, or if you watch the international meetings, they all have those earpiece, and then on the other side of that earpiece is the simultaneous interpreters who are making a translation on the fly with the minimized delay and the maximized quality. But of course, we cannot really get that data. So Graham Newvig, he collected that data for the Japanese English, but the collected data set is so small, you can't really expect that data to be able, data to allow us to train this kind of gigantic, let's say 100 million parameter neural net. So what we did was we just trained a neural machine translation system as usual. Nothing changed except that the encoder is going to be unidirectional. We trained it and then fixed it. And on top of that, we trained another neural net that is again recurrent, that is going to look at the internals of the underlying neural net. So it's going to look at the previous decoder's hidden state, previously decoded symbol, target symbol, and the source context. So that's going to be the observation to this new neural net. And then based on that, this neural net is going to decide whether to wait for the next source word or to start writing the translation. So if it says that, okay, wait, or the read, then it's going to wait for the next word. If it says write, then it's going to write out the translation at that moment instead of waiting for the end of the source sentence. And we can now then decide on our reward however we want, but we just made it as a combination, some kind of weighted combination between the delay and quality. And because it's just a reinforcement learning problem, we use a stochastic policy gradient. And then if you think about it, it's a gigantic state space or the environment we have. The observation is at least three-dimensional vector. And then it's not MDP, so it's a recurrent neural net that's going to look at the full episode so far. And then it needs to make a binary decision every time step. And the time step goes often like 20 to 30 steps. So it's the 2 to the 30. But the nice thing is that we could train it very, very easy. Well, if I said very, very easily, Jiatao is going to go crazy. But it was easier than we expected. And then the reason why is that because the underlying neural net was trained so well, what happens is the whole problem, if you worked at the actual sentence level, sentence space, is an extremely sparse reward situation, right? Because if you just randomly sample any sentence, it's very likely that that's just really nothing. That's not even a sentence. But what happens is that by letting the underlying neural machine translation system make the abstraction of the whole state space, what happens is that even if this neural net, the additional decoder, is going to make some mistakes, the underlying neural net is going to make sure whatever is generated is going to look reasonably sentence-like. And then that gives a very nice reward for the decoder to learn from. So let me show you one example. So this is the neural translation system we trained to translate from the German to English. And then in the usual neural translation, what happens is that you're going to wait all the way to the end of the sentence and then start generating the whole translation. Now, we take this network, we don't touch the network, but we train the decoder on top of that that's going to make a decision of whether to wait or write. And then the arrows actually indicate that the blue arrows are for the read or the wait, and then red arrows are to write. And then we see that this network has learned to wait about halfway, start generating, wait once, write once, wait once, write twice, wait twice, write twice, and so on. And then you see that the translation is essentially perfect. And then again, we never gave the network when to wait or when to write because we didn't really know ourselves. And then somehow we were able to train this model very well. And then we can essentially see that the delay, which can be formulated as the area above this, let's say, curve, is much smaller than the original neural machine translation system. So, and then we thought, okay, can we push the idea a bit further? How much further can we push? So we started with the same neural machine translation system because training these models takes so much time, so we try our best to reuse it over and over. So we used the very same neural machine translation system. And then we decided that, okay, so our trainable decoder, which in this case is a feed-forward neural net, is going to intercept the signal that is the previous hidden state and the previously decoded word and the context vector from the source sentence. It's going to read those roughly, let's say, 3,000 dimensional vectors, do some computation, and then it's going to inject back the signal. So it's going to inject the signal back, which is going to be about 1,000 dimensional vector. And then we train the trainable decoder to maximize whatever the reward we want to gain. We can maximize blue, we can maximize perplexity for the greedy decoding or whatever you want, really. It's just a RL problem, right? And then, of course, it's an extremely difficult RL problem. It's like potentially the worst possible control problem you can continuous control problem you can think of, because again, the observation space is 3,000 dimensional or more, and then the action space is again 1,000 or 2,000 dimensional continuous vectors. It's really difficult problem. So we decided to use the deep deterministic policy gradient algorithm from the, who proposed that algorithm? I guess David Silver, right? David Silver and others, in order to train this model. Let's look at some of the details. So what we had was a very simple feed-forward neural net that's going to take as input previous hidden state, previously decoded symbol, as well as the context vector, and then generate the output. And then we had to use the critic, which is going to be recurrent neural net, that's going to read the generated sequence, as well as the ground truth in order to approximate the score. And then based on that approximation, we're going to get the learning signal for the actor, which is the trainable decoder. So a lot of details, but one thing to notice here is that the deterministic policy gradient didn't really work for us, so we had to make some adjustment where the critic's validity is going to be taken into account. If you're interested in that, we can talk about it offline. And then once it's trained, we're going to just throw away the critic and then use the actor to do the decoding. So what we noticed was that if we train this kind of trainable decoder to maximize blue, then we're going to get better blue scores. If we train it to maximize perplexity, then we're going to get the good perplexity, except for in the case of finish. We're trying to figure that out. And then for any other type of the reward, we could just simply train it. It takes about a few hours to train this kind of model because network is so small. And still it works always whenever we want it to maximize some reward because it is working in the space of the pre-trained neural net. If it works on the space of the original sentence, it really never works. Everyone has to do some kind of pre-training or simultaneous training. And then in this case, we just train a very small network just for a few hours, and then suddenly we have a new decoder with the existing network. But of course, more work is definitely needed because not because of this idea is not working, because the model-free reinforcement learning just doesn't work in this kind of high-dimensional space. It just fails so easily. So that was for the neural machine translation. And then so far, what we've seen is that, one neural net using another neural net, right? So both of them are trainable. But what if one of them is not really trainable? So we decided to look at training a neural net to use the non-trainable fixed black box module in the context of the question answering. So this is mainly done together with my PhD student, Rodrigo Nogueira. So if you think about building an end-to-end question answering system, you can think of it's a very high level view. Like it doesn't really mean much. But you can think that okay, we're going to have some module that's going to receive the query and then tries to understand what the query is about. And then that module is going to ask the retrieval module or the search engine that, okay, get me some of the relevant documents or some knowledge about the question. And then based on the question and the retrieved documents, the answer selection module is going to say, oh, okay, so these are the relevant ones, right? So some kind of re-ranking. And then based on the selected relevant ones and the question, the answer synthesis module is going to synthesize the answer. Now the top three ones are very, very trainable. We can always train them. Actually, people do know how to train all those modules. But the fourth one, the retrieval module, is a bit problematic. We don't really know how to train it, and even if we know how to train it, scalability is an issue. And then as the knowledge source grows, it's difficult to train a retrieval system that doesn't need to be retrained every single day and still cope with a new type of information. So we decided to tackle this problem from two directions. First is the neural query reformulator, because that retrieval module is black box. We want this Q module, the query processing module, to be able to change the query so as to maximize the recall from that retrieval system. And then there's the machine comprehension and the answer synthesis. I'm not even going to talk about it because I don't know how to do that. If anybody tells you that they have the solution to it without showing you the paper, they are again lying. All those, so many liars, right? Yes. But anyway, so neural query reformulator. So our idea was that, okay, we're going to train this reformulator that's going to first look at the original question, and then original question and some of the candidate terms returned by the search engine over the Wikipedia. And then it's going to generate a new query that's going to go into the actual search engine. And then search engine retrieves some of the documents, and we score the recall rate against the ground truth, and then that is going to be used as a reward. So we train the reformulator to maximize that reward. It's again a very hard RL problem. I think as soon as the RL researchers do their job and then get me some awesome model-free reinforcement learning algorithm, I think all my problems are going to be solved right there. Why is it difficult? Because the observation space is again gigantic, as well as the action space is pretty gigantic as well. It's again 2 to let's say 200 or something. And then it's completely partially observed in the sense that we have absolutely no idea what the search engine is doing. So think about, let's say, oh, because I'm at the search engine company here, actually, I can ask you, so you probably can tell me. So what is the thing that search engine maximizes? My guess is that the search engine probably maximizes the ad revenue eventually. No? No? Well, you can say yes, like it's okay. Right? And then that is precisely not what we want to maximize, right? Our objective in this case is to maximize the recall of the relevant documents, not the ad revenue. So what it means is that this problem is difficult because we don't have any access to the search engine. Well, you do, so you can do it very well. So we used a policy gradient. It was a bit of a pain to do all these things, but it turned out that, again, we can train this model well as soon as we use some kind of existing language model or the word embedding vectors from another resource and then use it as a part of the reformulator. Once we have this network, actually the code and the data is all available online in our GitHub page. Once we have that, we decided that, okay, so what can I do to make it complete, right? So I need this answer selection module, but I'm pretty sure RL is not going to help me. So I was going to, okay, let's collect the data ourselves. So many of the existing machine comprehension data set, except for the very few recent ones, such as the Trivia QA as well as the MS Marco, existing machine comprehension data sets are not the ideal ones that we want to work with. So let's say DeepMind, CNN, or Daily Mail data sets are not really ideal. Why aren't they ideal? The reason is that they start with a passage, create a question and answer pair out of it. What it means is that the passage is too clean. And then if you use the search engine, if you build a search engine, you know that the search engine is never going to be perfect. They're going to return me a lot of irrelevant documents, and then a lot of documents are not going to be clean, and then a lot of things are just going to be these sponsored links. So they are not really realistic. So we decided to build a search QA data set using the question answer pairs from the Jeopardy. So we took all those question answer pairs, about 200,000 of them, query Google the question, and then augment the retrieved information or the snippets in order to build a data set. So we ended up with about 140,000 question answer snippet tuples. And then for each of the question, we have about 20 to 50 snippets. And then it's super realistic. If you look at it, people can solve it, but still have hard time because there are so many irrelevant noisy information. And then again, the data set is available online. And then we saw that the humans can do much better, but the neural nets are also doing okay. Not that great though. And then our goal back then, so this was like the beginning of the April type of thing. And then from there on, we were like, okay, we're going to take about 2 weeks of break because we spent so much time and then Google was blocking our IP constantly. And then we were like, okay, we're going to take about 2-3 weeks of break. And then we're going to combine the query reformulator together with the answer selector, right? That's the ultimate thing. And then about 3 weeks passed, and then Google in Zurich, so they have the information retrieval team there, did exactly what we wanted to do. What they did was they downloaded the search QA dataset, trained the underlying Q&A module called BiDef, and then that model is just neural net that's going to read the passage question and then select the answer out of it, and then they treated it as a black box. They just fix it, never touch it, and they trained the reformulator that's going to read the question and then generate the reformulator question that's going to be passed to this underlying black box Q&A model. And then this Q&A model is going to give the reformulator an answer. And then based on that, it's going to, like trying to maximize the accuracy. And then, this slide, this happened again. So somehow there are numbers here, but it never shows up. It only shows up in my screen. I don't understand. But what happens is that when they train this BiDef model, which is just a neural net, let's say machine comprehension model, on the search QA data set, you get about 35, let's say, F1 score. But once they train this reformulator on top of this, they can get about 45, 46 F1 score. And then that's actually a surprising thing in a sense that so far people have been trying so hard to change this Q&A system, right? So, I want to get a better neural net that's going to solve the problem better. But it turned out another way to approach is to let the question answer system as they are, because you probably have a lot of things available there. You can learn to use it better. And then that learn to use better seems to be pretty effective, especially in the case of this question answering. And I have absolutely no idea how Buck and others, were able to do it in 3 weeks, but they are Google. I guess they have the amazing resources. So a few more relevant research directions in this first is the communicating neural net. So at the end of the day, it's going to be the pool of the neural net modules, and then they need to talk to each other in order to exchange information as well as to solve a problem. In that direction, Rob Fergers at NYU, as well as the Shimon Weisen at Oxford, and my group as well, we've been working on it quite a lot. And then multimodal processing is kind of must, because all those different modules of the neural nets are going to look at the environment through a different lenses. And then those lenses are going to be the different modalities. And then at the end of the day, what we really need is going to be the planning or the program synthesis, let's say, algorithm. I have a bunch of things here, modules here. In order to solve a task A, how am I going to use those modules in what order and by how? So in that direction, Google DeepMind has been working quite a lot on it. And then they proposed something called Neural Programmer Interpreter. And then NYU and Facebook people, as well as Rich Sutton from 1991, was thinking about the forward modeling. And then you can actually go all the way to optimal control. And then more recently from Google and Google DeepMind, they've been thinking about building a gigantic mixture of experts network as well as a progressive network. So there are a lot of things that we need to do. So to conclude the first part, so this is what we do. We have the environment, and then we have an expert who's going to collect the data, annotate the data, and then train a neural net to solve that problem that expert ran into. And then once the training is over, user is going to just interact with the neural net. But now what we need to build in general is we need to think about how to build that kind of system where we're going to have multiple neural nets, and then each of the neural net is going to implement a certain function. And then those neural nets are going to work together with the existing black box algorithms that we have already built over, let's say, 40 years. And then all those modules are going to interact with the environment in their own ways. And then how to train the whole thing, that's going to be a big question that we need to pursue. So that was the high-level view of how the machine learning and deep learning should probably go on to. And then I'll just go a bit briefly in detail in about 10 to 15 minutes on the more specific topic of the neural-machine translation. So when I talk about the neural-machine translation to a lot of people, they tell me that, well, neural translation is a third wave in the machine translation. But I tell them that, that's completely wrong. Neural translation was the second wave in the machine translation, and the phrase-based system or the statistical-based system was the third wave, except that the NeuroMT was completely forgotten right after it was proposed. In fact, Professor Bob Allen, who's now at Yonsei University in Seoul, he proposed this kind of neural machine translation system in 1987 at the very first international conference on neural net. He trained the model to do the English to Spanish translation. It kind of worked. He used the word error rate, and then it was like average word error rate of 1.3 words. I actually emailed him, but he didn't answer. So if you stop by Yonsei University, just knock on his door, because he kind of was the first person who tried it out. And then right afterward, Chrisman at CMU proposed something that looks extremely similar. Then he called it dual-ported RAM architecture, and then he again applied to the English-Spanish translation. And then on the test set, which was only 50 sentences, in fact, training set was also 50 sentence pairs only, 75% of sentences were correctly translated. But I mean, the 100 sentences, that's too small, right? And then the whole thing was forgotten for about 5 to 6 years. And then simultaneously, from two groups in Spain, one from Valencia and the other from Alicante, proposed something that looks extremely similar to what we are doing these days. But again, it got completely forgotten. I actually met Mikhail Forcada in one of the conferences, and he was like, yeah, I knew that we were right. Just we didn't have enough computation back then. So, in a sense, the neural machine translation is the second way of the translation that is just reviving again these days. So what is the modern neural machine translation? Up until 2006, especially Holger Schunk has been working on, how to plug in the neural net language model as a post-processing of the statistical machine translation system. It worked okay. And then the Jacob Devlin and others, as well as other groups in 2013-14 proposed, let's incorporate the neural net as a part of the log linear model of the statistical MT system. And then, of course, Jacob Devlin was able to show amazing improvements on the Arabic English translation and Chinese English translation. So this has been a kind of darling of neural machine translation for 2-3 years, actually about 2 years. Now even Jacob doesn't do this. Jacob just do this fully neural machine translation. And then this is the part that I'm going to talk about. And then, we proposed this in 2014, 13, 15. And then one thing is that the improvements we were getting was pretty awesome. So early 2015 on English-German translation, we built a large vocabulary neural machine translation system. Our BLUE score was about 22. And then within a year, the improvements we got was about 5 BLUE scores. And then it was actually working better than any of the existing system. And in fact, this year, in the new translation tasks of the WMT, you see that every single system, for every single language pair direction, except for the, Finnish to English. No, actually, input, yes. Finnish to English. Somehow, Finnish is a very weird language. But except for that language pair, for every single language pair direction, NeuroMT was just beating the hell out of any of the systems. In fact, they were all beating the hell out of the Google Translate until recently. But Google Translate now rocks because it uses the neural translation system. But the important thing is that it was never our goal to make a neural translation system that's going to solve single language pair direction. It's never been a goal. It's not even interesting, right? So what we really want is, can we get a multilingual neural machine translation system? Because if you think about the single language pair direction, it's very uninteresting. And then there are some obvious fallacies for a lot of language pairs where we don't have enough resource. It just doesn't make any sense. Only if we can build a multilingual system, a single neural net that is going to be able to translate from any of the 170 languages to any of the 170 languages, now we can aggregate the whole resources available and train one neural net and then expect a positive language transfer. And in fact, I think I heard a rumor that the Google Translate uses only a single neural net to serve all those language pairs. So maybe you guys are doing it already, maybe. I don't know. So all right, what does the neural machine translation system do? I should skip this detail. But one thing we notice about the neural net is that it's extremely good at projecting the discrete sequence or some kind of input into the continuous vector space while preserving the semantics or the similarities. And of course, the semantics is defined with respect to the target task. But if you think about the translation system, as long as our targets are going to be all those different languages, what neural machine translation system need to do is to project any of the source sentence into this space so that it can be decoded into any other languages. What it means is that the similarity in terms of translation is going to be captured. And as long as we can train the whole thing so that the sentence in any of the languages is going to be projected into a shared common space, we can decode from that space into any of the other languages. Sounds pretty nice, right? I really like this. And then the continuous vector space is going to be stripped of hard linguistic symbols because the hard linguistic symbols cannot be contained there because you have to be agnostic to the actual language. So in starting from the 2015, people started working on this kind of idea. And then we actually decided that, okay, so we're going to build a neural translation system, attention-based one, that's going to translate from any of the 6 European languages to any of these 6 European languages while sharing a single attention mechanism. Now, a lot of people told me that, that doesn't make any sense because the alignment of the words is very specific to a pair of languages. On the other hand, what Orhan Firat and I thought was that, in fact, that's not true because that alignment part is the part that can be shared across languages, and then that is the part that allows us to learn a new language better if we know existing more languages. So, but of course, it's difficult to tell. If you go into the linguistics or the language education literatures, it's like 50-50. 50 of the people are going to say that raise your kid bilingual, and then the other 50 are going to say that no, you should teach your kid your mother tongue perfect first. So nobody has the answer to it. So we decided to actually test it out with a neural net. So we built this kind of scary-looking neural net, but it's in reality very simple. And then we just trained the whole thing with every single data from WMT, and then we were able to train this model, and then it was actually doing better than the single pair models. Why is it so? It's a thing that I don't have the answer to, but the hypothesis include, let's say, there is a better structure constraint on the continuous vector space because we let that space to be shared across the multiple language pairs. Or, because we use a smaller number of the parameters, maybe there is a regularization effect. And of course, it just means that we can go further. It's a neural net, right? Neural nets really don't care whether the input is language, input is image, input is some sensor measurements, or input is going to be something else. As long as you can project, you can let the neural net project whatever that input into the continuous vector space, then within the continuous vector space, the neural net doesn't really care what the original modality was. It's going to simply do the manipulation within it and then trying to decode it into another modality. So we noticed in 2015 that we can use the very same attention-based neural translation system for image caption generation. This is just an example of what kind of things the neural net can do. And then more recently, WMT decided to introduce a new track for the multimodal translation. So when we translate an image caption, is it going to be better if we let the neural net look at both the caption and an actual image that the caption is describing? So far, it's kind of debatable whether you do get the improvements, but we do see that some people started to report that, okay, in certain situations where the caption really does talk about something visual, then you do get the improvements. And at this point, we gotta ask a question, what is a sentence? Because as I said, neural net doesn't really care. Neural net, once it can project everything into the continuous vector space, it doesn't really care what the input is. So then what is a sentence? To neural net, to us, sentence is kind of sequence of words or the letter or something, but to the neural net, it's really nothing but a sequence of one-hot vectors, where the one-hot vector is a vector that consists of all zeros, except for the single element whose index corresponds to that vector's, let's say, original word. Let's say, in my vocabulary, the word cat is 2093 index, then my one-hot vector is going to have zeros everywhere, except for the 2093rd element, set to 1. So from the neural net's point of view, it doesn't really matter what the one-hot vector corresponds to. It can correspond to words, it can correspond to phrases, it may correspond to images, it can correspond to anything you can think of. Now, what does that mean? What it means is that we gotta think about this whole using neural net as a kind of removing all the constraints that were imposed by the existing systems. So in the case of when you build a statistical machine translation system with the table or the count-based algorithms, because of all those issues with the data sparsity and so on, you had to work with the words. But in the case of neural nets, because we know that as soon as the neural net projects any of those one-hot vectors into the continuous vector space, we don't have any issue. So can we just build a neural net that works on the sequence of characters or sequence of bytes or the sequence of bits or the sequence of strokes? So that's the thing that we need to think about instead of just blindly using it with the sequence of words. And then there are many reasons why we do not want to work with the sequence words. First of all, it's very inefficient, especially for neural net, to handle various morphological variants if we give a sentence as a sequence of, let's say, white space tokenized or the separated words. First of all, this is actually the words in Basque. So that's like the northern part of Spain. So that's, I think, the old house, new house, house behind, and so on. And then you see that they all share the very same structure. But from the neural net's point of view, those are going to be just 4 independent vectors, right? So 4 independent one-hot vectors. So it's not really the most efficient way to do it. And then second thing is that in a lot of languages, there are ways to make a completely new morphological variants. In the case of Arabic, does anybody speak Arabic here? So I copied and pasted over from my friend's email. That word means end to his vehicle. And then he was able to just make it up. And then anyone can make up a new morphological variant as they want. And then it's impossible to handle those kind of things. And then furthermore, in the case of Finnish and Turkish, there are a lot of compound words, like German as well. So for instance, this is kolmi vai kilowatti tunti. That's going to be 3,000 kilowatt per hour meter. And then that's just a one word. And then at the same time, the golme, which is the original form of the golmi there, that's 3, that's going to have one vector as well. So it's a very inefficient way to assign the different number of the parameters to different words because, clearly the first one has much more information compared to the second one. And there are some issues with the spelling issues. I highly recommend you to check out those workshops on processing historical language because historically there's been no such thing as the standard spelling. So they have been, let's say, working on that for like 30 years, how to normalize all those spelling issues. And then even then, the issue is that we don't really have a good segmentation or tokenization algorithms for every language you can think of. So it doesn't look like the words are a good way to go. So we can actually go for a lot of different ways. Let's take an example Korean sentence, right? So originally it's going to be 고양이가 침대 위에 누워 있습니다. Word level, subword level, character level, and fully character level. Of course, in the case of Korean, the character level is kind of, let's say, tricky, right? Are you going to go for the syllables or are you going to go for the actual letters? But it doesn't really matter from the point of view of neural nets because neural nets don't care, right? So to the neural net, this is going to be one-hot vector. To the neural net, that 고양이 is going to be just a one-hot vector. So as soon as we encode it into a sequence of characters or the something, one-hot vectors, the neural net doesn't really care. So what we did was that, okay, let's see if that's true because nobody was somehow doing it. So we took the source sentence as a sequence of subword units or the words. And then for target, we consider it as a sequence of very flat characters. And then we just train the existing model as it is without changing anything because somehow nobody tried it. I don't know why. So we thought we were going to try it. And then we noticed that it actually works better than working at the word or the subword level. And then we see that this attention map actually is able to map between a very different levels of representation between the source and target. And furthermore, of course, based on this, why stop here, right? We decided to go for the fully character level. So we're going to just forget about whatever the word that is. We're going to just take as the input sequence of characters. Blank spaces are going to be just characters, like the T is going to be character, everything is just characters, and then target is going to be again characters. But of course, the issue is that now the computation is problematic one, so we decided to introduce the convolutional neural net with the aggressive pooling in order to reduce the sequence size, sequence length, and then fit it into the standard model. Again, it turned out that in a lot of language pairs, like 4 language pairs that we have tried, the character-to-character model worked better. So why is that? That's a big question, right? Why is that the case? Why should it work better? Okay, working as well as the existing approaches, that's understandable. But why does it work better? It's because we have minimized any kind of prior knowledge, and then what we know about the language or the kind of inductive biases that we've been encoding into a neural net, somehow it must have been something wrong, not the correct one to do. So in this case, we have essentially stripped off of any kind of inductive bias or the prior knowledge we have, and then somehow it works better. There were some linguists, right? Yeah. Sorry. It seems like I think the Fred Jelinek may have been right. But so what does it do? So it turned out that our models are really good at, let's say, coping with the spelling mistakes and then working with the rare compound words, as well as some of those ironic words as well. So if you know German, this compound word, this kind of, let's say, worsening improvements, so that's kind of ironic word, that it doesn't really happen a lot. And then our model was able to translate it perfectly, while this subword level model was kind of, let's say, giving it up. But okay, but this is cute, but this is not really interesting, right? So what do we want to do? What we want is that we want a multilingual model. We want a single network that's going to translate from multiple languages into another language. So we decided to train this model, especially at the character level. It's really easy to share the same network across the multiple languages. And because we were working largely with the European languages, the network we could train was to translate from a sentence written in any of Finnish, Russian, Czech, German. There was one more. But anyway, okay, those to English. So we just trained one model without giving any information about what kind of, or in which language the source sentence was written in. And then we were able to test it with the kind of made-up sentence with the intra-sentence code switching. So this is a sentence that uses a bit of German, bit of Czech, bit of German, bit of Russian, and then bit of German. So it's a made-up sentence, but if you look at the bilingual speakers, it actually happens quite often. And then if you go into social media, a lot of people mix the different languages in a single sentence. And then the model that we train never saw that kind of sentence because those kind of sentences rarely occur in our training set. But the model was able to translate it perfectly because the network knows about all those different languages. And then because it saw all those different languages, it learned how to project the sentence written in any of those languages into the shared common continuous vector space from which a translation can be decoded. So this was really cool. It was unfortunate that there is no such, let's say, evaluation set, so we had to just do it qualitatively. But this may be the kind of answer to how to deal with those informal social media data if you want to translate it well. And then, of course, this is for translation, but it doesn't have to be for translation alone. You can do the question answering or even building those kind of chatbots. So as the final thing, so if you remember about the question answering, what was kind of the idea there? The idea was that we can train a neural net to use or adapt to the fixed black box search engine. And then we thought that, okay, can we use the search engine then for training as well? So if you think about what a parametric machine learning or non-parametric machine learning or the neural net is, if you think about the parametric machine learning, learning is effectively a process of compression. That is, we're going to train a neural net using a gigantic training data, right? We're going to do the training for weeks or for days. And then when we use it or deploy it, we're going to throw away the whole training set. So what it means is that the neural net needs to do both data compression, so it needs to compress all the relevant data from the training set, and then to do the pattern matching internally in order to solve a problem. And this seems to be a pretty difficult thing to do as the training set grows larger and larger, and then especially when the training set grows automatically on the fly. Because in that case, we have to retrain the model over and over, and that's not that great. So the idea is that can we actually remove the data compression part and then let the neural net only focus on the pattern matching part. So that is to make the non-parametric neural machine translation system. What we're going to do is we're going to bring the whole training corpus together with the neural machine translation system. And then every time there's the new input, we're going to use a very efficient text-based search engine to retrieve the relevant translation pairs. And then this translation model is going to look at both the current source sentence as well as the retrieved translation pairs, both source and target in that case, right? And then by training the model to do so, what this neural machine translation system or the neural net is going to do is to cope with the fact that we're going to get the additional information from the search engine using the training set, and then all it needs to do is to learn to fuse them instead of learning to compress the whole training set into the fixed number of parameters. So we built this system. It was pretty straightforward. So we got all those training set, and then we're going to let the Apache Lucene, which is the open source search engine, to index a whole training set based on the source sentence. And then this neural net is going to query this given source sentence, which in this case is going to be Jeon Futuarus or something. And then based on that, we're going to retrieve all those translation pairs. And then those translation pairs are going to be encoded into the key value memory net. And then based on the memory net contents, the decoder is going to retrieve the relevant information from it and then trying to get the next word's distribution. This is very much similar to how to train a neural machine translation to exploit the external knowledge, such as the knowledge base by the An et al., as well as the dictionary by Badana et al. And what do we get? What we get is that when the retrieved pairs are really similar, then the neural net actually knows how to exploit it as much as it can, and then the improvements on BLEU score is very high. When the retrieved sentence pairs are not that great, we get the 0 improvement. So there is a decrease there between 0 and 0.1, but that's not the number that you can trust because there's only like 12 sentences there that belongs to that. And then what happens is that qualitatively we notice that the higher consistency in writing style as well as the choice of the vocabulary. So for instance, in the source sentence, the leprosy, I hope that's the correct pronunciation, that was translated by the baseline model into the precise period. That's actually the correct, let's say, translation. But in the training set, if you look over and over, in this kind of situation, often that phrase is translated into exact deadline. And then because the neural translation system looks at the retrieved sentence pairs, it's going to use the exact deadline in order to generate the translation. And then indeed, the ground truth translation does use exact deadline instead of the precise period. So this is kind of non-parametric NMT that's, I think, is going to be really important for the personalization as well as the lifelong learning type of thing, because we can just add in the training, add in more examples into the training set without having to retrain the neural translation system on how to use them. So some of the other advances in Neuro Translation includes the discourse level machine translation as well as the better decoding strategy. I talked about the trainable decoding, but there are a bunch of other works on that. And then, of course, to make the linguists generally happier, people have worked on how to build a neural translation system that is better guided by linguistics. But I also wrote a paper together with Akiko Eriguchi from University of Tokyo, and then it's going to be presented at ACL. But both the first author as well as me, we are kind of unsure whether it's a good way to go, unfortunately. So yes, today, we talked about a lot of different things, but I think the one thing that if you want to take away is that I think we are at the point where we're going to make a next leap with the neural net and then artificial intelligence in general, and then that is going to that can only be done if we can build a gigantic system like we have done with the software engineering. So it's going to be a trainable, huge software system that's going to solve multiple problems. And then that's probably what Google is going to do, Facebook is going to do, Microsoft is going to do, and then probably Naver should as well. And then I'd like to thank all those companies that have sponsored my research, and also my industrial project partners, Samsung and NVIDIA. So now Naver needs to just send me some gift money as well, right? Yes. All right, thank you. That's it from me.
일단 첫 번째 질문은 아까 릴타임 NMT에서요. 그 막 리드 할지 라이트 할지 그런 게 나왔었는데 이게 리드를 원래 어텐션 베이스드 막 NMT에서는 일단 전체를 다 읽어서 거기서 이제 어떤 부분에 집중할지 했는데 여기는 처음에 이제 리드를 일부분만 이제 하는 거잖아요. 근데 나중에 이제 읽었더니 뭔가 지금 아웃풋에 있는 이제 버퍼 단어들 중에서 뭔가 바뀌어야 될 게 있을 텐데 다시 리와이트를 해야 되는 경우도 있을 텐데 저기는 이제 그런 연산은 이제 없는지. 네.
네, 저희는 그런 거를 넣지는 않았고요. 지금 저희가 하고 싶었던 세팅은 simultaneous interpretation이라서 한 번 얘기를 하고 나면은 얘기한 걸 다시 바꾸는 옵션이 없는 상황을 가정을 하고 있고요. 물론 지금 액션이 2개밖에 없는데 액션을 더 넣을 수 있겠죠. 예를 들어서 back off 같은 옵션이라든지 아니면 delete and rewrite 같은 옵션을 넣으면은 계속 할 수 있겠죠. 예. 근데 거기까지는 저희가 안 해봤어요.
네, 그다음에 마지막 질문은 이제 NMT가 기본적으로 슈퍼바이즈 러닝으로 하게 되는데 그러면은 하나의 어떤 문장이 다른 하나의 문장으로 꼭 매칭이 돼야 되잖아요. 근데 우리가 번역을 할 때는 하나의 문장이 여러 개로 번역이 될 수도 있는데 그게 제가 생각했을 때 요즘에 제너티브 애드버서리얼 네트워크를 통해서 이제 NMT를 하는 논문들이 나오는데 거기에 대해서는 이제 어떻게 생각을 하는지 그렇게 되면 이제 제너레이터가 이제 이 머신 트랜슬레이터가 되고 그게 꼭 어떤 타겟을 통해서 크로스 엔트로피 로스를 미니마이즈 하는 게 아니고 디스크리미네이터를 이제 속이는 쪽으로 학습을 하게 되면은 좀 슈퍼바이즈 러닝의 저는 이제 단점을 좀 극복할 수 있을 거라 생각하는데 이제 조경현 교수님은 어떻게 생각하는지 궁금합니다.
아 이거 겐으로 텍스트 제너레이션 하는 거 이거 함정 질문인데 말이죠. 예, 그러면 막 사람들하고 엄청 싸운다고요. 근데 왜 크로스 엔트로피로 한다고 해서 왜 답이 하나라는 건 아니죠. 왜냐면은 이게 컨디셔널 디스트리뷰션을 러닝을 하는 거니까요. 실제로 소스 센텐스를 주고 디코딩을 막 해보면 스토캐스틱 디코딩을 하면 여러 가능한 것들 막 리오더된 것들이 많이 나오니까요. 사실 이미 디스트리뷰션 러닝을 하고 있어서 이제 겐이 필요할 이유는 만약 우리가 이제 로스 펑션이 크로스 엔트로피라는 로스 펑션이 하는 거는 디스트리뷰션 러닝을 하는 건데 디스트리뷰션 러닝이 아니라 다른 걸 하고 싶다 하는데 로스 펑션을 모르는 상황에서는 개안이 필요할 수도 있겠죠. 근데 개안이라는 게 별게 아니고 액츄얼 크리틱 메소드라고 보면 되거든요. 다만 여기서 크리틱을 트레이닝 시킬 때 저희는 이제 크리틱이 실제 리워드를 프레딕트를 하게 되어 있는데 리워드를 프레딕트하는 게 아니라 주어진 지금 디코드된 센텐스랑 사람이 쓴 센텐스가 다른지 같은지를 디스크리미네이트 하는 게 크리틱이잖아요. 그러니까 이미 쓰이고 있다고 보면 되죠.
Hello. Okay. For the real-time machine translation model, I was overall wondering. So you mainly tried to incorporate an actor-critic model to model whether or not you should be reading, writing, or deleting everything. Wouldn't that be very similar to a memory model, or through a set of different LSTM gates? Or wouldn't that also be similar to skip gate connections inside a 2D array of LSTMs?
Wait, so can you tell me the question again? So what you're saying is that is it similar?
Like rather
To-
than
Mhm.
formulating as a reinforcement learning problem, why not just exploit the fact that LSTMs have gates to forget information, delete information, write information, and just use that instead?
Yep, that's a very good question. Yes. So the question was that so instead of training with the RL, because we use all those gated units, by looking at the gates, we may be able to actually exactly tell when to stop or wait for the next word or to try to write, right? But again, we're going to have at least thousands of those gates, and then which of those gates corresponds to which kind of information, we don't know. But now this one is effectively using that information, right? This agent learns to use that.
Right, because this seems like some sort of more weighted attention, but this attention, rather than using it as a set of attention weights, rather you're just trying to formulate a set of gates instead.
Yeah, so I mean, you can make this model however you want. It doesn't really matter, right? So the idea here is that even then, if you don't have the precise data that was, let's say, annotated or collected for your decoding objective, now it becomes really difficult problem anyway, however you build a neural net in, right? So what it means is that here we use the reward that is some kind of weighted combination of the delay and quality, and then that can be arbitrary as well. So in order to cope with those kind of arbitrary nature of the decoding objective, we need to learn to maximize that.
So
Of
in
course,
that
you can do it
case-
better with the better neural net, right? Yeah.
So then is there a sole motivation on why exactly reinforcement learning for this sort of problem?
Sorry?
Why exactly reinforcement learning to model this portion of the network?
Oh, because our reward is non-differentiable. And then also the action is discrete. And in that case, we don't really know how to do the backpropagation, right?
Okay.
그 QA 모델에 비해서 이제 번역 모델의 경우에는 그 어떤 이제 개념 자체를 메모리에 저장하거나 개념을 이해하는 것이 아니라 단순히 이제 A 언어에서 B 언어로의 매핑을 주로 찾는 모델이 많다고 생각하는데, 근데 이제 그럼 실제로 이제 애플을 사과로 번역할 때 애플이 뭔지 모르고 하는 모델이 지금 대부분이잖아요. 근데 이제 애플의 개념을 이제 가르침으로써 번역 태스크를 향상시킬 수 있는 모델로의 방향은 혹시 생각하고 계신가요?
네, 잠시만요. 뒤로 좀 가보면 나올 것 같은데요. 일단 두 가지로 볼 수 있을 텐데요. 좀 더 하이 레벨에서 보자면은 사실 예를 들어서 이런 그 멀티모더 트랜슬레이션을 한다고 했을 때, 예를 들어서 뭐 소스 센텐스 캡션이 이제 퀘스천이라고 해보죠. 퀘스천이라고 하고 이미지 같은 거나 다른 이제 컨텍스트를 거기 캡션에 들어가 있는 단어들을 활용을 해서 뭐 knowledge base 같은 데서 뽑아와서 같이 넣어줄 수 있겠죠. 그렇게 하는 방법이 하나가 있을 거고요. 그리고 또 하나 이제 아주 최근에 보면은 지금 이 디마가 이번 몬트리올에서 구글 팀이랑 해서 퍼블리시한 페이퍼에 보면 단어가 들어왔을 때 그 단어가 아주 프리퀀한 단어가 아니면은 딕셔너리 데피니션을 이용을 해서 월드 벡터를 뽑아내는 식으로 하는 게 있죠. 근데 그렇게 해도 문제가 이게 트랜슬레이션 같은 경우는 생각보다 그렇게 복잡한 문제가 아니거든요. 그리고 트랜슬레이션 자체가 굉장히 리처럴한 트랜슬레이션을 해야 되는 게 뭐 오브젝티브 때문에 큰 도움은 보통 안 되더라고요. 근데 이제 특수한 케이스에 그런 이제 컨셉이 중요한 경우에만 좀 도움이 되고요.
네, 저는 그래서 오히려 이제 센텐스 페어들이 그 많이 있는 트랜슬레이션을 이용해서 이제 QA로 이용하는 방식으로 그 미닝의 임베딩을 가져오면 어떨까 생각을 해봤는데요. 그래서 이제 인코더, 디코더 모델이 두 개가 있고 이제 하나가 영어에서 한글, 한글에서 영어가 있으면 이제 각각의 리컨스트럭션 에러에다가 이제 Z 스페이스를 같이 미닝이라는 피처가 같으면은 얘가 이제 미닝을 캡처할 수 있는 벡터가 되지 않을까 하는데 혹시 이런 어프로치가 된 게 있나요?
그 얼마 전에 그 페이스북 AI 리서치 페리스에서 홀걸 슈엔케가 이제 센텐스 레프레젠테이션을 할 때 이제 멀티링구얼 이 인코더 디코더 모델을 이용을 하면은 뭐 잘 된다 그런 쪽으로 페이퍼가 있었는데 아마 그 페이퍼랑 그 페이퍼에서 사이트한 다른 페이퍼를 좀 보면 좋을 것 같습니다.
예, 감사합니다.
네, 죄송한데 앞쪽 질문을 좀 드리고 싶은데요.
네.
그 뉴로사이언스 처음에 말씀을 하셨고
네.
결국 사람의 어떤 그 인지 과정 혹은 어떤 내부에서의 퍼셉션이나 커그니션 쪽의 과정을 생각을 하면은 사람 같은 경우는 에피소딩 메모리랑 워킹 메모리랑 별도로 구분되어 있고 펑션도 좀 다르다고 알려져 있는데 지금 이쪽 그림에서는 뭔가 그 하이레벨한 모듈 네트워크가 따로 있고 실제로 그 아랫단에서 돌아가는 좀 이제 뭐지 퍼셉션에 가까운 쪽의 네트워크가 따로 있는데 그러면은 좀 더 훨씬 앱스트랙션 된 레벨의 어떤 정보가 위쪽에서의 어떤 네트워크에서 또 별도로 학습이 될 텐데 사람은 이게 메모리라는 개념이 있으니까 위쪽에서 하이 앱스트랙트 된 레벨에서의 그 학습된 것들이 메모리 형태로 이렇게 익스터널 메모리 형태로 저장되는 건지 아니면은 파라미터 형태로 저장되는 건지 잘은 모르겠지만 현재 이 모델 구조에서는 그 별도의 익스터널 메모리를 생각을 하고 계신 건지 아니면은 파라미터만 학습하는 모델 구조를 생각을 하시는 건지 궁금합니다.
그 non-parametric neural MT를 보면은 이제 거기 같은 경우 이제 실제 트레이닝 example을 다 가져가고요. 사실 그 페이퍼랑 비슷한 게 이제 구글 딥마인드에서 오리오 비냐에 한 이제 뉴럴 에피소딕 컨트롤 같은 경우도 보면 에피소드들을 다 이제 메모리에다 넣어놓고 계속 그것도 non-parametric으로 계속 긁어오는 형식이죠. 그러니까 여기 있는 각각 모듈들이 딱히 뭐 무조건 parametric 모듈은 아니고요. 이제 그런 식으로 위에 에피소드를 저장하고 있는 메모리도 있을 수 있고 실제 트레이닝 익샘플들을 바로바로 저장한 애들도 있을 수 있고요. 왜냐하면 궁극적으로는 여기 있는 모듈들 중에 몇 개는 그런 메타 러닝 모듈이 될 거니까요. 과연 어떻게 진행이 될지는 정확히 모르겠지만 그 부분도 다들 다른 방식으로 하고 있어서 그러니까 이제 사실 메타 러닝 모듈 그리고 에피소딕 컨트롤 이런 것들이 다 들어가게 되겠죠. 궁극적으로.
사실 그 부분을 얼마나 잘 하느냐에 따라 가지고 성능이 굉장히 많이 달라질 수 있을 것 같다고 생각이 되는 게
네.
결국은 메모리에는 제한 사실 사람이 좀 완전 다른 기작이지만
네.
메모리를 어떻게 쓸 거면 어디를 실제로 트레이너블한 옵저버블 데이터 인스턴스로 쓸 거면 어느 부분을 이제 앱스트랙션 시켜가지고 걔네들을 또 다른 형태로 저장을 시킬 거며 하는 부분을 결정하는 거에 따라서 어떻게 보면 태스크에 따라도 완전히 다를 수도 있다고 생각이 되거든요.
네네. 예, 맞습니다. 그래서 지금 메모리도 따로 모듈로 떼놓은 거죠. 예, 아무래도 그 메모리라는 거랑 이제 메모리가 아닌 실제 엑시큐션한 모듈들이 어떻게 인터페이싱하는지 자체가 굉장히 중요한 문제가 될 것 같습니다. 근데 이제 사람하고는 다른 게 저희 이제 디지털 이게 소프트웨어다 보니까 메모리 같은 경우는 사실 완벽한 메모리를 저희가 만들 수가 있죠. 그렇게 했을 때 어떻게 보자면 슈퍼 휴먼으로 가는 길은 메모리 같은 걸 잘 쓰는. 네. 맞습니다.
예, 뭐 없습니다. 그럼 제가 질문 예, 뭐 아주 기초적인 질문일 수도 있는데 아까 사실 그 워드백이라든지 아니면 센터에스 자체를 벡터 스페이스로 매핑하는
네.
문제 가지고 이제 사실 아까 질문하셨던 어떤 미닝에 대한 컨셉에 대한 그 벡터 자체가 어떻게 보면 하나의 컨셉이라고 볼 수도 있는데요. 근데 사실 실제로 그 이 뉴럴 네트워크에서 다루지 않고 있는 게 어떤 로직이라든지 인과관계라든지 아니면 어떤 포함 관계라든지 이런 것들은 사실 벡터로만 어떤 포인트로 나타내기 어렵잖아요. 근데 그런 거에 대한 뭔가 그 벡터 스페이스 상에서 그런 것들을 그룹핑할 수 있는 개념이라든지 이런 것들에 대한 연구가 있을까요?
예, 그 맞습니다. 그러니까 어떻게 보자면은 그러니까 아까 말씀드렸던 것 중에 이제 그 프로그램 신테시스가 이제 들어가는 건데요. 프로그램 신테시스를 할 때 두 가지 큰 문제가 있는데 첫 번째는 이제 인풋이 이런 그런 퍼셉션 인풋이라고 하면 노이지하고 제너럴라이즈를 해야 되니까 인풋에서부터 어떤 프로그램 신테사이즈된 프로그램의 심볼로 어떻게 매핑을 할 거냐의 문제가 있고요. 그 부분은 지금 보니까 이제 딥러닝이 막 하고 있는 거죠. 뉴럴 프로그래머 인터프리터 같은 걸 보면은 인풋은 어떻게 주어지고 그리고 프로그램이 어떻게 엑시큐트 돼야 된다고 해놓으면은 그 사이에 실제 인풋과 엑시큐트된 프로그램 그리고 엑시큐션 코어가 이제 러닝이 되는 식이죠. 이제 그런 부분을 보면은 여전히 벡터 방식으로 하는 게 이제 퍼셉션 인풋을 어떻게든 인코딩을 해야 되니까요. 맞지만 실제 뭐 프로그램을 또 찾는다 하면 그 부분은 이제 컴비네이셔널 서치를 해야 되니까요. 그 부분을 이제 어떻게 할 거냐. 그 부분에 대해서 이제 예전에 막 굿 올드 패션 AI 하던 분들이 많이 해놓은 알고리즘들이 이제 와서 이제 다시 쓸 수 있겠죠. 이제 퍼셉션한 인풋이 들어왔을 때 그 인풋을 가지고 뭔가 로지컬한 오퍼레이션을 하겠다. 그리고 로지컬한 오퍼레이션을 찾고 싶으면은 이제 컨벤셔널 서치와 이 딥러닝을 러닝하는 거를 같이 찾을 수 있을 거고요. 하지만 궁극적으로 이거 관해서 이제 상해 지난주에 있을 때 얀 르쿤하고 얘기를 했는데 얀이 생각을 하는 거는 어차피 컨비네이셔널 서치라는 거는 안 된다는 거를 돌려 말하는 거다. 할 수 없다는 거를. 그렇다면은 근데도 사람들은 어떻게든 코드를 다 짜잖아요, 저희들은. 물론 대부분의 사람은 못 하고 이제 일부 사람만 할 수 있는 거지만 그걸 보면 어떻게 보자면은 그런 combinatorial search도 과연 discrete space이긴 하지만 다 continuous space로 보내서 그 안에서 뭔가 gradient descent 같은 optimization을 하고 다시 프로젝트 백 하는 게 아니겠냐. 그렇게 보는데 그쪽은 저 잘 모르겠네요. 네. 그러니까 이게 뭔가 모든 게 다 합쳐지는 거는 궁극적으로는 합쳐지게 될 것 같습니다. 네.
감사합니다. 자, 어쨌든 그 상당히 모시기 어려우신 분이었는데 그래도 저희가 오셔서 이렇게 좋은 강연 해주셔서 너무 감사드리고요. 마지막 다시 한번 또 박수 좀 부탁드리겠습니다. 네.
감사합니다.
네.